In this lesson, we want to talk about polynomial functions and their graphs. All right, before we jump into the lesson, let's just go over a few basic definitions. These are things we're going to refer to constantly in this lesson. So if we have something like this right here, it represents a polynomial function of degree n. So you see here we have that n is a non-negative integer and represents the degree of the polynomial. We are also going to say here that a sub n, so this guy right here, is not allowed to be equal to 0. So just think about this with a simple example. Let's say you have f of x is equal to, let's just do something like a quadratic so it's easy, so 2x squared minus x minus 1. If you think about the degree of the polynomial, what is it? Again, it's the highest exponential power, so it's going to be a 2. So that's all we're saying there. That n right there is representing the degree of the polynomial. And remember, when you have a polynomial, you want to make sure that the exponents on your variables are whole numbers only. You can't have a negative, you can't have a fraction or something like that. So that's why this says n is a non-negative integer, which is basically a whole number. 0, 1, 2, 3, 4, so on and so forth. So let me get rid of this and let's come down here. So we have a sub 0, a sub 1 through a sub n are known as the coefficients of the polynomial. Now, a lot of people get confused about this. So if you have this is the constant term. So we have a sub 0 is known as the constant term or the constant coefficient. So why do you say a coefficient there? What is it the coefficient of? If you had something like, let's say f of x is equal to, let me use another example. So let's go 3x squared minus 2x plus 5. I can legally write this right here as x to the power of 0. Remember, x to the power of 0 is 1, and 1 times 5 is still 5. So that's why you're able to say constant coefficient there. A lot of people just say the constant or the constant term, just so you know that there's different ways to see it, and you might get that in your textbook. So then a sub n, so that's this guy right here, is going to be known as the leading coefficient. So you hear that a lot today. The leading coefficient is the coefficient of the term where x is raised to the highest power. So if the polynomial function is written in standard form, so descending powers of x, it will be the leftmost coefficient. A sub n and then x to the power of n is known as the leading term. So that's going to be this whole thing together. This is the leading term. So the leading term is the term where x is raised to the highest power. Again, if the polynomial function is written in standard form, so descending powers of x, it will be the leftmost term. All right, just to make sure we're all on the same page, we're going to do a quick example. So I have a little table here. We have the polynomial function, the degree, the leading coefficient, the leading term, and then the constant term. So let me go slow for the first one, and then for the next ones, we'll just blow through it. So we have f of x is equal to, you have your negative 6x to the 4th power plus 3x squared minus 2. So this is written in standard form. So basically, when we look at this, the degree, again, you're looking for the highest exponential power. So that's this guy right here. So that's the 4. The leading coefficient is the coefficient for the leading term. So that's going to be this negative 6 right here. Then the leading term, that's the whole thing. So negative 6x to the 4th power. And then the constant term, again, that's going to be this guy out here. So it's going to be negative 2. Now, for the rest of them, let me erase this. We'll just go through it really quickly. So we have f of x equals 7x cubed minus 4x squared plus 3x minus 8. So the degree, again, that's just going to be 3. The leading coefficient, that's going to be 7. The leading term, again, that's the whole thing. So it's 7x cubed. And then the constant term, that's the negative 8. Then for this one, f of x equals 9x squared minus x plus 4. The degree is going to be 2. The leading coefficient is going to be the 9. The leading term is going to be the whole thing, so the 9x squared. And then the constant term is the 4. Then for this one right here, we have f of x equals negative 2x minus 5. The degree is 1. Why is the degree 1? Again, if you write this out, so f of x equals negative 2x minus 5, what's the exponent on that x? It's going to be understood to be a 1, so that's why the degree is 1. The leading coefficient is negative 2, then the leading term is the whole thing, so negative 2x, and then the constant term is the negative 5. All right, so at the beginning of this section in your book, they're going to start by talking about transformations of monomials. This is something that we pretty much already know how to do. We studied graphing transformations in great detail already, so I'm just going to run through this and do one example only. So a monomial is a polynomial that consists of just a single term. So something like 5x to the 6th power, or negative 3x cubed, or something like 1/3 x to the 4th power. So each there would be an example of a monomial. because it's a polynomial with one term. Now, just some general information. When we talk about the graph of a polynomial function, so something like f of x equals x to the power of n, where n is even. So we're talking about something like f of x equals x to the 4th power, the 6th power, the 8th power, the 10th power, something like that. We're going to say this has the same general shape as the graph of f of x equals x squared. So we know that's the parabola shape. As the degree of the polynomial n gets larger, the graphs will be more flat around the origin and steeper everywhere else. We can observe this with f of x equals x to the 4th power. So for all of the graphs today, I left you a link for Desmos if you want to view it on your device. Maybe the screen is a little bit hard to see, so you can just pause the video and go to those links. So right here, if we look at this guy and let's call it green, that's your f of x equals x squared. Again, that's our basic parabola. And then we have g of x equals x to the 4th power. So that's the guy in red. You'll notice that this guy right here is flatter around the origin and then steeper everywhere else. Now you can go into that Desmos link that I gave you and you could type in x to the 6th power, x to the 8th power, x to the 10th power, so on and so forth. And you're going to see that it gets more and more flat around the origin as this exponent gets larger and larger and it gets steeper everywhere else. All right, so similar to what we saw above, the graph of a polynomial function f of x equals x to the power of n, where n is odd now, so let me highlight that, has the same general shape as f of x equals x cubed. Again, as the degree of the polynomial n gets larger, the graphs will be more flat around the origin and steeper everywhere else. We can observe this with f of x equals x to the 5th power. So the guy in green is your f of x equals x cubed. We know what that looks like. And our guy in red, that's g of x equals x to the 5th power. Again, you can zoom in on Desmos to make this more apparent, but this guy right here in red, your g of x function, it's flatter around the origin and then it's steeper everywhere else. So if you want to type in x to the 7th power, x to the 9th power, so on and so forth, you'll see that it keeps getting flatter and flatter around the origin and steeper everywhere else. Okay, let's look at an example where we're asked to graph something and it's just a transformation of a basic monomial that we're used to working with. So we have something like f of x equals x cubed. We know what that graph looks like. And then we have g of x equals 1/2 times the quantity x minus 3 cubed plus 1. So we have studied graphing transformations in great detail. This should not be something that you can't do at this point. You know that for the horizontal transformations and the vertical transformations, they do not impact each other, so you can do them in any order. But if you have multiple vertical transformations or multiple horizontal transformations, remember you have to do those in a specific order. So what I'm going to do here is just work left to right. That's going to be fine here. So I'm just going to say the first thing is this 1/2 that's multiplying this guy right here. And again, you can say that that gives me a vertical compression by a factor of 2. I know a lot of people don't like that. They'll say, I want to say vertical shrink by a factor of 1/2. The different terminology there has the same meaning. You're taking the y value and you're either dividing it by 2 or multiplying it by 1/2. So use whatever terminology you want to say. I'm just going to state that there's a vertical compression. So a vertical compression by a factor of 2. Let me fix that. Now, the second thing, I'm going to go inside the parentheses. Now, this is going to impact x here. And remember, with the transformations with x, the horizontal ones, you have to undo what's being done to x. Here we have x minus 3 on the inside. So to undo that, I want to add 3. So that's going to shift me to the right by 3 units. So I'm going to say we're going to shift right by 3 units. Let me fix that. And then when we get back on the outside here, we have this plus 1. Again, that's vertical. So we're going to say that we want to shift up by 1 unit. So just shift up by 1 unit. So it's important that you understand that this one and this one, so the vertical compression, or again, you could say vertical shrink, by a factor of 2, or in the case of vertical shrink, you'd say by a factor of 1/2. This one has to be done first, and then this one would have to be done second. The order of the vertical transformations would matter here because you have 2 of them. But this horizontal one here is not impacted by these, so you could do this in any order. You could do it last, you could do it first, it does not matter. What I taught you in that lesson was you can just work left to right. Again, as long as this part right here was in factored form. Here we don't have anything to factor out. It's very, very simple. We only have one operation in there. We're just shifting to the right by 3 units, so it's not really a big deal. So just keep that in mind. You might need to go back and review that lesson. But I think most of you spent a lot of time on this, so you pretty much can remember the steps that we have here. So if I make a little border here and I say, okay, for f of x, we have some x comma y. Well, then when we go to g of x, what is that going to become? Well, it's going to become your x, all you're going to do is add 3 to it. So it's x plus 3. And then your y, you're going to divide it by 2, or again, multiply it by 1/2, whatever you want to do. And then you're going to add 1 to that. And that's pretty much all it is. Let me go ahead and grab this and come down here. I've already pre-drawn everything for us. So the guy in green, that's your f of x equals x cubed. Again, you should recognize that graph. Your guy in red, that's your g of x equals 0.5 times the quantity x minus 3 cubed, and then plus 1. So thinking about a point like 0, 0, again, where's that going to go to? 0 plus 3 is 3. And then here you'd have 0 over 2, which is 0, plus 1, which is 1. So this 0, 0 is going to go to 3, 1. Then something like, let's say 2, 8, that's going to go to 2 plus 3, that's 5. Let me fix this 3 here. Doesn't look so good. And then this would be 8. So 8 over 2 is 4. 4 plus 1 is 5. So this 2, 8 is going to go to 5, 5. And then the last point we'll do, you can do as many as you want. We have negative 2, negative 8. So that's going to go to negative 2 plus 3, that's going to be positive 1. And then negative 8 over 2, that's negative 4. Negative 4 plus 1, that is negative 3. So this negative 2, negative 8 is going to go to 1, negative 3. So again, with those points, you're able to easily sketch this guy. You know what the general shape is, and you can put more points in if you need to, but I think this is enough to get a good graph going. All right, now let's get into graphing a polynomial function that's not a monomial, so something where we can't just use graphing transformations. And to do that, we need to understand what we're talking about when we say smooth and continuous. So we have smooth and continuous definition. So polynomial functions of degree 2 or more have graphs that are smooth and continuous. When a graph is referred to as being smooth, it means the graph has only smooth, rounded turns. So in other words, the graph of a polynomial function can't have a sharp turn, which is a turn where the direction is changed suddenly. Okay, we're going to talk a lot about this when we get to calculus and we get into derivatives. When a graph is referred to as being continuous, it means the function can be graphed without lifting the pencil from the page. So in other words, there are no breaks or holes in the graph. So let me give you some examples of graphs that are not polynomial functions. So this one right here, if you look at it, you have this sharp turn. You want only smooth, rounded turns. This is a sharp turn. There's a sudden change in direction. Then when you look at this one right here, it is discontinuous. If I'm graphing this guy, I've got to pick my pencil up and come up here to continue the graph. So we know when we look at this, these are not the graphs of a polynomial function. When we look at the graphs of a polynomial function in general, you're going to see something like this. And they have different shapes, but when you look at this, this is an example. See how you have a smooth rounded turn right here? Same thing here, same thing here. You have a smooth rounded turn here and here. So that's what you're looking for when you're talking about the graphs of a polynomial function. All right, let's talk a little bit about the graphs of polynomial functions and something known as the end behavior. So the end behavior of a polynomial function describes what happens to the function as x approaches both positive and negative infinity. You might hear this in your book as x increases without bound, that just means approaches positive infinity, or decreases without bound, that means x approaches negative infinity. Now the notation for that, this is x increases without bound, or x approaches positive infinity. And then this one right here, this is x decreases without bound, so x approaches negative infinity. The two functions given below, so f of x and g of x, will have the same end behavior. This is due to the influence of the leading term. So this guy right here is exactly the same as this guy right here. So which is commonly referred to as the dominating term when x is large in terms of absolute value. So that means approaching positive infinity or approaching negative infinity. The other terms are going to be insignificant in size. So to prove that to you, I have a little simple example. So we have f of x equals x cubed minus 4x squared plus 2x plus 3, and then g of x equals x cubed. So there's two ways that books usually show this. Some of them use the factor it out approach, which I'm doing here, and some of them will use a table. So you can do that as well. So basically with the factor it out approach, you're going to take this guy right here, whatever it is, and you're going to factor it out. So we're going to show this as f of x equals x cubed times the quantity 1 minus 4 over x plus 2 over x squared plus 3 over x cubed. And then you're just going to think, well, what would happen as x gets really, really large? So as x approaches positive infinity, what's going to happen to this right here, this 4 over x? It's going to get really, really close to 0. 2 over x squared, really, really close to 0. 3 over x cubed, really, really close to 0. And that would be true as x approaches negative infinity as well. So what you're going to have is 1 minus something very close to 0 plus something very close to 0 plus something very close to 0. So basically this guy is going to approach 1 on the inside of the parentheses. It won't be exactly 1, but it's going to get really, really close to 1. And so that would be multiplied by x cubed. So it's going to be really, really close to x cubed. So this guy and this guy will be really, really close in value as x approaches positive infinity or as x approaches negative infinity. Again, the other way you can do this is you can use a table and you can just start plugging in things that are larger and larger. And you can see that for yourself. I'll let you do that method on your own. I've always preferred this factor it out approach. Now let me show you the graph here, and you can make the window different if you want just by playing around with it on Desmos. So this guy in red, that's our g of x equals x cubed. We know what that looks like already. And then in green, that's the f of x equals x cubed minus 4x squared plus 2x plus 3. What's happening to the y values or the function values as x approaches negative infinity? So as it decreases without bound. So I would say that y is going to approach negative infinity. Let me fix this. As x approaches negative infinity. And then let me fix this infinity sign here. I'll make that a little bit better. And then up here, if we think about what's happening to the function values or the y values, well, y is now going to approach positive infinity as x also approaches positive infinity. So for this type of graph, a lot of times your book will say it falls to the left and rises to the right. So falls to the left and rises to the right. You could also use this notation as well. So since the domain of a polynomial function is the set of real numbers, we can use this end behavior to describe parts of the graph we can't sketch. For an odd degree polynomial function, the graph will have the opposite behavior at each end. We just saw that a moment ago. We had it falling to the left and rising to the right. Whereas an even degree polynomial function will have a graph with the same behavior at each end. So if this is our polynomial function, well, what's going to happen is you can use this as a little memory guide. If your leading coefficient here, your a sub n, is positive and your n value is odd, your graph is going to fall to the left and rise to the right. If the case is where a sub n, this leading coefficient, is negative, well, now it's going to rise to the left and fall to the right. Now, when n is even, what's going to happen is if, again, the leading coefficient here, a sub n, is positive, it's going to rise to the left and rise to the right. And then when your a sub n, or your leading coefficient, is negative, again, when n is even, it's going to fall to the left and fall to the right. So notice that in this column right here, so again, this is when n is odd, you have opposite behavior. So this is falling to the left and rising to the right. This is rising to the left and falling to the right. Then when n is even, again, you have the same behavior. So rising to the left and rising to the right, and then down here, falling to the left and falling to the right. So as we discussed above, the end behavior of a polynomial function is determined by the degree n and the sign of the leading coefficient a sub n. Some books refer to the process of finding the end behavior as the leading coefficient test. You will definitely see that, since we're only analyzing the leading coefficient and nothing else. You don't have to worry about anything else in that process. So this is a good image just to get a recap of what's going on. So let's say that your n is odd and your a sub n, your leading coefficient, is positive. Again, we saw an example of this one earlier. Well, y is going to approach negative infinity as x approaches negative infinity, and y is going to approach positive infinity as x approaches positive infinity. Again, we don't know what happens in the middle here. We just know the end behavior. For this one, again, you could say it falls to the left and rises to the right. Now on this one over here, you have a sub n, again, the leading coefficient, is less than 0. So in this case, it rises to the left and falls to the right. So y approaches positive infinity as x approaches negative infinity. And then down here, you have y approaches negative infinity as x approaches positive infinity. So if you're having trouble remembering this, just remember f of x equals x cubed, or you can even do f of x equals x if you want to, and think about the end behavior of this guy. So if you get something where the degree is odd and the leading coefficient is positive, just remember it falls to the left and rises to the right, just like your f of x equals x cubed. Then this one you could use if the degree is odd and the leading coefficient is negative. Here the leading coefficient would be -1. So it's going to rise to the left and fall to the right. All right, so let's look at an example. Here we're given f of x equals x to the 5th power minus 3x cubed minus x minus 1. So if we think about the end behavior of this guy, if we were to graph it, we're going to look at the leading term, which is x to the 5th power, or you could write that as 1x to the 5th power. So the leading coefficient is going to be 1, which is positive, and the degree is 5. So that's going to be odd. So that tells me the graph falls to the left and rises to the right. So if you want to look at the graph, here's the f of x equals x to the 5th power minus 3x cubed minus x minus 1. Again, it falls to the left and rises to the right. So another example, here we're given f of x equals -2x cubed minus 5x squared minus x plus 1. So the leading term now is -2x cubed. The leading coefficient would be -2, which is obviously negative, and the degree is 3, which is odd. So here, the graph rises to the left and falls to the right. So again, looking at this guy, the f of x equals -2x cubed minus 5x squared minus x plus 1, we can see it rises to the left and falls to the right. So the other scenario is going to be where n is even, and in this case, remember, on each n, you're going to have matching behavior. So in other words, with this one, where your a sub n is greater than 0, or you could say the leading coefficient is positive, well, y is going to approach positive infinity as x approaches negative infinity, and then y is going to approach positive infinity as x approaches positive infinity. So for this one, you could say the graph rises to the left and rises to the right. See how it's the same at each end. Then over here, let's say a sub n is less than 0. Again, that's just the leading coefficient if it was negative. Well, now y is going to approach negative infinity as x approaches negative infinity. And then we can say y approaches negative infinity as x approaches positive infinity. So for this, you could say the graph falls to the left and falls to the right. If you're having trouble remembering this, just think about f of x equals x squared. So this is going to be for the case where the leading coefficient is positive, and again, the degree is even. So something like this. So for this one, it rises to the left and rises to the right. Now the other one, let's go with f of x equals negative x squared. Again, you could write that as f of x equals negative 1 x squared, just to make it crystal clear. So you have an even guy right here for the degree, and now the leading coefficient is negative. So this is going to be, again, flipped upside down. We know this is a reflection across the x-axis. And if we look at this, the graph falls to the left and falls to the right. All right, let's look at some examples of this one. So f of x equals 4x to the fourth power minus 2x squared minus 1. Well, the leading term here is this 4x to the fourth power. The leading coefficient is 4, which is positive, and then the degree is also going to be 4, which is even. So for this one, again, you could just think about f of x equals x squared. That guy looks like this. So we know the graph rises to the left and rises to the right. So for this, we have f of x equals 4x to the fourth power minus 2x squared minus 1. Again, clearly you can see it's rising to the left and then rising to the right. All right, another example. So f of x equals negative 2x to the sixth power minus 3x cubed plus x squared plus 2. So the leading term here is negative 2x to the sixth power. The leading coefficient is negative 2, which again is negative, and the degree is 6, which is going to be even. So for this one, again, think about the upside down parabola. So the graph falls to the left and falls to the right. Again, when you're thinking about the end behavior. So looking at this guy, here's your f of x equals negative 2x to the sixth power minus 3x cubed plus x squared plus 2. Again, it falls to the left and falls to the right. Okay, now we want to talk about the shape of the graph near a 0. So this is another piece of the puzzle if you're trying to sketch the graph of a polynomial function. So at this point, we know how to find the zeros of a polynomial function. So we spent a lot of time on that. Recall that a 0 or a root of a polynomial function is a solution to the equation f of x equals 0. So in other words, you can replace f of x or your y with 0 and solve for x. And the real solutions to the above equation are the x-intercepts of the graph. So let me highlight real solutions there. We already know that we might have non-real complex solutions. Those guys are not going to be x-intercepts on your graph. So it's really important to understand that. So when we have a 0 of even multiplicity, so something like 2, 4, 6, something like that, the graph will touch the x-axis and turn around. In other words, it touches but does not cross the x-axis there. Let me stop for a moment and let me come up to the example here. And I'm just going to rewrite this. So this is f of x is equal to, it's x plus 3, but we're going to rewrite that as x minus a negative 3. So it's crystal clear that the 0 there is negative 3. This is quantity squared, and then we have this x minus 2. So we know that here you would have a 0 of negative 3 with multiplicity 2, and then you'd have a 0 of 2. So we know that we would have an x-intercept at this guy right here, which is negative 3, 0, and then you'd also have one right there, which is 2, 0. Now I want you to notice that this exponent here is even. It's 2, so that means, again, this is a 0 of multiplicity 2. Notice that this graph comes up and it touches there and then turns back around. It does not cross through like this one does. Let me go back. When we have a 0 of odd multiplicity, so something like 1, 3, 5, 7, so on and so forth, the graph will cross the x-axis. Additionally, graphs will flatten out near zeros where the multiplicity is greater than 1. So if you have a multiplicity of just 1, it's just going to cross straight through. It's not going to flatten out. So looking at this, here the 0 is 2. Again, you have that x-intercept that's 2, 0. Notice it just crosses straight through. It does not flatten out in any way, shape, or form. Now let me show you this, which is just what we expect when we have repeated zeros. So I'm going to start off with a case where the multiplicity is going to be greater than 1 and your exponent is odd. So a factor x minus k raised to the power of m, where m is greater than 1. So it's not 1, it's not multiplicity of 1. It would be a multiplicity of, let's say, 3, 5, 7, something like that, yields a repeated 0, x equals k, that's just coming from right there, of multiplicity m. Again, that's coming from right there. When m is odd, again, 3, 5, 7, 9, so on and so forth, the graph crosses the x-axis at x equals k. But again, because the multiplicity here, given by this m being greater than 1, we're going to have the graph flatten out. So it's not going to cross straight through like you saw in that example earlier. So it's going to look something like that or something like that. Now, the other case, when m is even, so let's say something like squared, the 4th power, the 6th power, so on and so forth, the graph touches but does not cross the x-axis at x equals k. Again, because the multiplicity here is greater than 1, you're going to see this guy flatten out. Now, the greater the multiplicity, the more it's going to flatten out. Now, let me read this, and then I'm going to go back to that example and explain what's going on. So when you have a 0 of even multiplicity, so let's say it's 2, 4, 6, 8, something like that, the sign of your polynomial function is not going to change from one side of your 0 to the other side of your 0. And that's because when you square something, the result is always non-negative. You're either going to get 0 or something that's positive. If that doesn't make sense for me reading it, it will make sense in a moment when we do the example. So we would say that this means that the graph is going to turn around at the 0 of even multiplicity. Again, because there's no sign change from one side of the 0 to the other side of the 0. If the 0 is of odd multiplicity, so it could be 1, 3, 5, 7, so on and so forth, then the sign of the polynomial function is going to change from one side of the 0 to the other side of the 0, which causes the graph to cross the x-axis at that 0. So it's very important you understand this if you want to make an accurate graph. Let me go back up. All right, so specifically using this example, let's see if we can understand why this is turning around here, but crossing through here. Why is that the behavior of this guy? Well, if you think about setting up some intervals, something like anything that's less than -3, so from -infinity to -3, both are excluded there. We're using the open interval notation. And then between -3 and +2, again, both are excluded there. And then anything larger than 2. Remember that we're multiplying these guys together to get the y value. So you plug something in for x, plug it in there, plug it in there, multiply these two guys together, you get your y value. Well, if you think about this factor x minus 2, this is going to be negative in this interval here and also this interval here. Because something like x minus 2, actually we can just say, where is that greater than 0? That's very simple to solve. You add 2 to both sides of the inequality, this cancels, and you get x is greater than 2. So it's only going to be positive for x values that are greater than 2. It would be negative here and negative here. So what that tells me is that if I look at this other factor here, which is x plus 3 quantity squared, this guy is always going to be non-negative. It can be 0 when x is -3, so that's right there, but it's going to be positive everywhere else because of the squaring. So okay, if this guy is multiplied by this guy, then I already know, again, just using my little sign chart here, that anything to the left of -3 will have a negative times a positive, which gives me a negative. So I'm going to be below the x-axis, again, where the y values are negative. Then when I think about being in this interval right here, well, again, this guy's positive, this guy's negative. So a negative times a positive gives me a negative. So I'm below the x-axis. My y values are negative. So think about what's happening here. I'm negative, 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 negative. I come up to the point where x equals -3. And so you get, again, let me write this out. So this would be -3 plus 3 quantity squared. And then times you would have -3 minus 2. All I'm doing is plugging in for x there. So this right here would be 0 squared, which is 0, times -3 minus 2. That's going to be -5, which is going to be equal to 0. So this goes from negative, negative, negative to 0. And then on the other side of that, what's happening is we're going back to having a positive times a negative again. And so we're going to be negative, 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 negative. And that's going to continue until we get to an x value of 2. When you get an x value of 2, again, this guy is going to be 0. And then when the x value is greater than 2, well, now you have a positive times a positive, which gives you a positive. So this is negative, negative, negative. It turns to 0. And then once we're greater than 2, we're going to be positive. So notice that you had a sign change from this side of 2 to this side of 2. So that's why we're crossing through. But when we looked at this one right here, there was no sign change. We were negative, 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 and then we went to 0. We never go to positive, then we go back to negative, negative, negative. So that's why this guy is going to come up. It's going to touch and turn around, and then this guy's going to come up and now go through. So hopefully that does make sense. We're going to do another example so you can pause the video and think about that one on your own. Let me go down to that one. So here we have f of x equals the quantity x minus 1/2 cubed, then times the quantity x plus 2 squared, then times the quantity x minus 2. So we know that we would have a 0 of 1/2 and the multiplicity would be 3. We have a 0 of, this would be -2, the multiplicity would be 2. And then we have a 0 of +2, the multiplicity would be 1. Let's write that out. So for the zeros, we have 1/2, the multiplicity, and I'll just abbreviate that, is 3. Then we're also going to have -2, and the multiplicity, so the multiplicity there, would be 2. Then lastly, this is x minus 2. You could put a 1 there for clarity. So let me just say that the last 0 here would be 2. A lot of times if the multiplicity is 1, we don't write it. But just for clarity here, I'm just going to write it. So the multiplicity is 1. So let me make a little border here. And let's think about what we would expect. So these are the x-intercepts. So we're going to have 1 at 1/2, comma, 0. Now the multiplicity for that 0 is 3. So I know that this is going to cross through the x-axis there. And I also know because the multiplicity is 3, it's greater than 1. So it's going to flatten out near that 0. Then you also have one of -2, comma, 0. So the multiplicity here is 2. So that's even. And so this guy is going to touch and turn around. And also this will be a little bit flattened out because the multiplicity is 2, which is greater than 1. Then you're also going to have this guy right here, which is going to be 2, comma, 0. Now the multiplicity here is 1. So again, when you think about that, it's just going to cross straight through and it's not going to flatten out because the multiplicity is just 1. So let's go down and confirm what we just said. So this guy right here, that is your -2, comma, 0. Again, coming from this right here, x minus a -2, quantity squared. Notice that it's going to touch and turn around. When we look at this guy right here, this is 0.5 or 1/2. Again, that's coming from right here. We know it's going to go through, but notice that here it flattens itself out a lot. And that's because the multiplicity is 3. If you have something like 3 or 5 or 7 like that, it's going to flatten out when you go through on that 0. Let me label this. You can put 1/2, comma, 0, or again, you could use 0.5 if you want. That's just going to be personal preference. And then this one right here is going to be for 2, comma, 0. Again, the multiplicity there is 1. Notice that it doesn't flatten out there. It crosses through, but it just crosses straight through. It doesn't flatten out in any way. So that's just something you need to understand when you're looking at your zeros and you're planning on how you're going to set those up when you sketch your graph. Okay, so before we actually get into sketching the graph of a polynomial function, we need one more piece of the puzzle. So we're going to talk about turning points. Your book might title this as local maxima and minima. So polynomial functions often have turning points. So where the function changes from increasing to decreasing or from decreasing to increasing. So these turning points will be referred to as a local maximum point, also known as a relative maximum point. You might hear that as well, when the function takes on a greater value than any nearby points. So you're thinking about the y value. Is it larger than any nearby points? That's going to form what we call a hill. And I'll show you that in a moment. And a local minimum point, also known as a relative minimum point, when the function takes on a lesser value than any nearby points. So is the y value smaller than the y value of nearby points? So that's going to look like a valley. Let me just go to this little example here. Local maximum points, you have points A, so that's this right here, and C on the graph. Notice that the y value here is greater than the y values around it. We are not saying that it's the largest y value on the graph. It's just what's in the local viewing window. That's how you're thinking about this. This forms a hill. This forms a hill. Another way to think about it, remember earlier on, we talked about increasing and decreasing those intervals. I drew a little guy that was walking. So let's just say this guy is walking, and right now you are increasing. So right here, you're going to change that over, and now you're going to be decreasing. So where we change here is at this point A. So that forms what we call a local maximum point. We're changing from increasing to decreasing. Now this guy's going down. And you could do the same thing if you wanted to draw it. You're increasing here, and then at C, you're going to change over, and now you're going to start decreasing. All right, the other one, we talk about local minimum points. So points B and D on the graph. Notice how that looks like a valley here and a valley here. Again, we're not saying that the y value here is the smallest on the whole graph. It's just in a local viewing window. You can see that the y value here is less than those around it. Same with the y value here. It's less than those around it. If we think about, again, doing this with our walking guy, you're changing. So right here, he is decreasing, decreasing, decreasing. When we get to that point B, we're changing over to increasing. So now this guy is going to be walking up. So just think about it that way. If you're changing from decreasing to increasing, that's going to form a local minimum point. If you're changing from increasing to decreasing, that's going to form a local maximum point. All right, so when you hear the terms maxima and minima, these are just the plural forms of the words maximum and minimum, respectively, coming from Latin. The local maximum and minimum points on the graph of a polynomial function are called its local extrema. So this is something that you'll definitely see in this section. A lot of times for your test or for your homework, you're going to be given a graph and you're going to be told to find the local extrema. I have a note here. So without the use of some basic calculus, so this would involve derivatives, it is usually not possible, or at least extremely impractical, to find the actual turning points for a polynomial function when the degree is greater than 2. So what I'm talking about there is that you don't have a graph. So you're not using Desmos, or you're not presented with a graph or something like that. And they just give you the function and they say, hey, go ahead and find the local extrema. That's something we're going to be able to do once we get to calculus and we learn about derivatives. All right, before we move on, I want to stop here and just cover a very common source of confusion. So when you deal with local extrema, and you'll deal a lot with this in calculus, you want to understand the question that you're being asked, because it can be asked in different ways, and so you would give different answers. What we've done so far is we've been working with points. So I would say something like, what are the local minimum points? So those are x comma y. Or what are the local maximum points? So those are x comma y. So those are turning points, and this is in the context of graphing a polynomial function. We need points. So you have to understand the difference between how things are being worded. So I have here, what's the difference between where a function has a local, or again you could say relative, maximum or minimum, and the local, or again you could say relative, maximum or minimum. So if f of x sub 1, remember that's a y value, that's us plugging in x sub 1 for the function and evaluating. So f of x sub 1, that's a y value or a function value. So if f of x sub 1 is greater than all other values of f, and we're talking about y values there, near x sub 1, then f has a local, or again you can say relative, maximum at the input value x sub 1. So again, if they're asking you where, you're going to see the keyword at used when you answer. So it's at, and you can give your x value. Now, sometimes the teacher will say specifically that they want the point. So then you give the x comma y. Then we have the local, or again, you could say relative maximum. So we're talking about that there is the output value. So the f of x sub 1, so that y value there. So we could say that f of x sub 1 is a local, or again, you could say relative, maximum value of the function. So just keep that in mind. And it's the same thing for this one when we talk about a minimum. So if f of x sub 2 is less than all other values of f near x sub 2, then f has a local, or again, you could say relative, minimum at the input value x sub 2. So again, if they're asking you where, you're typically saying it's at, and you give the x value. Then you could say the local, or again, relative, minimum is the output value. So that's your f of x sub 2. So we could say that f of x sub 2 is a local, or again, relative, minimum value of the function. So just keep that in mind if you get questions about local extrema. Okay, one more thing before we look at an example. So a polynomial function of degree n has at most n minus 1 turning points. So let's say the degree was 3. The most number of turning points you would have would be 3 minus 1, which is 2, with at least one turning point between each pair of consecutive real zeros. So keep that in mind. I have a note here. Be careful here, as we are only saying that a polynomial of degree n has at most n minus 1 turning points, not that it will have n minus 1 turning points. So a polynomial function of degree n may have less than n minus 1 turning points. So you may get something that's a 5th degree polynomial that does not have 4 turning points. We are only saying here that it has at most 5 minus 1, which would be 4 turning points. Okay, let's look at an example real quick. So I have this graph already drawn. So let me write this out. It's a little bit hard to see. So f of x is equal to, you're going to have 1/4 times the quantity, x minus 1, and then times the quantity, x minus 3 squared, and then times the quantity, x plus 2. Again, I've given you this on Desmos. Your degree here, if you want to go through and simplify, it's going to be 4. And so you can see you have 1, 2, 3 turning points, but it doesn't always work out that way. But we know that, again, if the degree is 4, it's going to have n minus 1, so that would be 3, turning points at most. But it doesn't mean it has 3, just at most. If I asked you, what are the local minimum points and what are the local maximum points? Again, I'm asking for points, so I want x comma y. So I'm going to write out local minimum points. And then let me write out local maximum points. Again, your teacher may ask for this in a different way. I am specifically asking for x comma y. They may want the y values just depending on how they phrase this. That's why I spent so much time on that little reading earlier. But if I look for the local minimum points, so I'm looking for where it's going to go from decreasing to increasing. So this is decreasing and then changing to increasing. So this is going to be -1 comma -8. So that's going to be a local minimum point. So -1 comma -8. So we're going to come back up here. Forget about this for right now. We're going to come back down. So this right here, again, we're changing from decreasing to increasing. So this forms a little valley here. So another local minimum point, you're going to have that at 3 comma 0. So you have two of those here. One right there, again, you're changing from decreasing to increasing, and then one right there, again, changing from decreasing to increasing. Now, in terms of your local maximum points, you just have one here. So it's going to occur right there. You're changing from increasing to decreasing. Again, this is forming a little hill. So that one's going to be 1.75. And this is an approximation. So let's just say it's about 1.099. All right, now let's wrap things up. I'm going to give you a little procedure for creating a rough sketch of the graph of a polynomial function. So I want you to keep some things in mind here. You are not a computer. You are not going to make a perfect graph, and you don't need to. As we move forward in math and we get into stuff like calculus where we can take derivatives and things like that, we will be able to make a more accurate graph because we'll understand where the turning points are. Even when we get into calculus, it's still not going to be perfect. You can always use a graphing calculator like a TI series or Desmos, some online graphing calculator, if you need a perfect graph. This is just about learning the concept. So here I'm going to start off by saying that we can use the leading coefficient test to find the graph's end behavior. So what's happening as we go to the very far left and what's happening as we go to the very far right. So just the end behavior. Then we're going to find the x-intercepts by solving the equation f of x equals 0. So again, we're looking for the real solutions to that equation. So those guys are going to be the x-intercepts. If you have a non-real complex solution, remember that's not going to be an x-intercept. If k is a zero of even multiplicity, keep in mind the graph touches the x-axis at x equals k and then turns around. If k is a zero of odd multiplicity, the graph crosses the x-axis at x equals k. And we know if the multiplicity of k is greater than 1, the graph flattens out near k comma 0, so at that x-intercept. Then we want to find and plot the y-intercept. So find the y-intercept as 0 comma f of 0. This right here is not always practical. Sometimes if you're working on something, you might get a y-intercept that's something like, let's say 0 comma 500. You can change the scale of your graph, but it's not always practical. So I would say this one right here, you want to know what it is just to see if you're on the right track, but sometimes you won't be able to fit it in unless you really change the scale. All right, we have use symmetry when available to sketch the graph. So you can't always use this. So y-axis symmetry, f of negative x equals f of x. Origin symmetry, f of negative x is equal to the negative of f of x. So sometimes you can use that to help. And then we have use test points within the intervals formed by the x-intercepts to find the sign of f of x in the interval. So since the graph of a polynomial function is continuous, remember no holes or breaks, the values of f of x are either always positive or always negative in a given interval. What do I mean by that? Well, the interval you're creating is going to be between the x-intercepts. So we're not going to have a y value of 0 unless we're on an x-intercept. So if you're between those x-intercepts, you're either above the x-axis or you're below the x-axis, again, because the function is continuous. So when the values are positive, we are above the x-axis, right? The y values are positive there. When the values are negative, we are below the x-axis. Again, the y values are negative there. Then you can use the maximum number of turning points of n-1 to check the graph. Remember, it doesn't have to have n-1 turning points, but that's the maximum number that it can have. So if you have a function with a degree of 5 and you have 7 turning points, you did something wrong. Okay, let's look at the example. So here I have f of x equals the quantity x minus 3 squared, and then times the quantity 2x minus 1, and I've put this right here as f of x equals 2x cubed minus 13x squared plus 24x minus 9, if you want to see it being simplified. So what is the first step? We're going to think about the end behavior. So the leading coefficient is 2, which is positive, and the degree is 3, which is odd. So that tells me, again, just think about f of x equals x cubed. It falls to the left and rises to the right. So if you look at the little graph, and I'm going to fill the rest of it out in a moment, you see here I have that it falls left and rises right. And you don't have to worry about it. I know it's going to come something like that. Just put this to the far left and to the far right like this, and just show your teacher you know what's going to happen. We need to get the x-intercepts. And again, for that, you're just going to say x minus 3, quantity squared times 2x minus 1 is equal to 0. Well, one of your zeros is going to be 3 with a multiplicity of 2. So let me write the zeros here. You're going to have 3, and then the multiplicity is 2. And then the other one, you set 2x minus 1 equal to 0. So 2x minus 1 equals 0. Add 1 to both sides of the equation. This cancels. You get 2x is equal to 1. Divide both sides by 2. This cancels. You get x is equal to 1/2. Now, if you want to do this, and some teachers will tell you to, you can actually factor this. Let me put like this. You can pull a 2 out. So if I pull a 2 out from here and put it out here, well, what happens is I divided this by 2 and I just get x. 2x over 2 would be x. And then I have to divide -1 by 2. So this is -1/2. So that's another way to do it if you want, to just write everything in the form of x minus k. And so you have 1 0 of 3, which again has a multiplicity of 2. And then you have another 0 of 1/2, which I'm just going to write. Normally we don't, but we'll just say the multiplicity is 1. So we know the x-intercepts here would be, this one is 3, 0. And again, it's going to touch there and turn around. And this one would be 1/2, 0. And there it's going to cross straight through. So here is your 3, 0. Again, it's going to touch and turn around. And then here is your 0.5, or you could say 1/2, 0, and it's just going to go straight through. We need our y-intercept. So how do we get that? Again, you plug in a 0 for x. So f of 0 would be equal to, again, all this would just go away because 0 cubed is 0, 0 times 2 is 0. 0 squared is 0, 0 times -13 is 0. 0 times 24 is 0, so you just have 0 minus 0 plus 0, that's just 0. So you're really just left with that -9 there. So you would get 0, -9, which in this case would fit on a graph. It would not be a problem. So 0, -9, that's going to be down there. All right, so at this point, I'm going to set up a little table and just get some additional points. So you'll see here that I have interval, I have the x value that I'm going to pick, and then the f of x or the y value that I'm going to get. So where am I getting these intervals from? Again, like I talked about in the procedure, it's just coming from the x-intercepts. So at the x-intercept, we know that the y value is 0. So that's going to be at an x value of 1/2, and then also at an x value of 3. But if you're not at an x-intercept, well then we know that the y value is either going to be positive or it's going to be negative, meaning I'm going to be above the x-axis or below. So you're going to pick something in the interval where x is less than 1/2, and you're going to see if I plug that in, do I get something that's positive, meaning I'm above the x-axis, or negative, meaning I'm below the x-axis? Then you're going to do the same thing. You're going to pick an x value between 1 and 3, and then you're going to do the same thing, and you're going to pick an x value that's greater than 3. So let's come back down, and I have here some values are rounded. So in this interval where x is less than 1/2, I'm just going to pick an x value of 0.295, and the y value here is about -3. Not exactly, but pretty close. Then in the interval between 1/2 and 3, the x value I'm going to pick is 1. The y value I'm going to get out is 4. Then in the interval where we're greater than 3, we're going to pick an x value of 3.78. And this right here, we're going to get a y value of about 4. Again, this is rounded here, so it's not exactly 4, but it's pretty close. So I've added this 0.295, -3, this 1, 4, and this 3.78, 4. So that gives me more points. Again, that allows me to sketch something that's more accurate. So what we can do here is a little estimation technique. And I would start with something like f of 1, which equals 4. Again, that just comes from the point 1, 4 that we just found. Again, I'm trying to find a local maximum. Let me go back real quick, just so this is crystal clear. Again, at this point, we know the graph is going to come up like this. So we know we're going to be increasing, and at some point we're going to switch over. That would be the turning point, and we're going to start decreasing. And then here we're going to have a local minimum. So this is a turning point, and then we're going to come back up. We're going to start increasing again. So what we need to figure out is where this guy is going to go from increasing to decreasing. So where does it change over? That's the turning point. That's the local maximum. So if you start with this f of 1 equals 4, now what I'm going to do is look at f of, and again, I'm just going to pick 1.25. You could do f of 1.1 or f of 1.05. It's just a matter of what you want to do. So f of 1.25, this is equal to 4.59375. So this y value is larger than this y value. So then I'm going to do that again. We have f of 1.3. This equals 4.624. So this y value is larger than this y value. Then I'm going to do that again. So we have f of 1.35. So that's equal to 4.62825. So this y value is greater than this y value. And then I'm going to do that again. So f of 1.4 is equal to 4.608. So now this y value is smaller than this y value. And if you look at f of 1.5, this equals 4.5. So this y value is smaller than this y value. So what does that tell me? That tells me that this guy right here, which gives me the largest y value, so in other words, 1.35, 4.62825, out of what I looked at, that's a good place to turn. It's not going to be exact, but it's a good place to turn because you're looking for where this guy's going to go from increasing to decreasing. Look at your y values. You have 4, then you go to 4.59375, then you go to 4.624, then you go to 4.62825, and then you start dropping off. So you go to 4.608, 4.5. So I don't know exactly where this happens, but I can just say that this 1.35, 4.62825, that's a good place to turn. Now, in the future, when we get to calculus, we'll be able to find the exact turning points, but we need derivatives for this. So something like the derivative of our polynomial function, that's f prime of x is equal to 6x squared minus 26x plus 24. You would take that and set it equal to 0 and solve. So we know how to do that already. So you get x equals 3. And then 4/3. Now, if we come back, again, we already know the 3 one, that's a local minimum. But the one we didn't know was the 4/3, which is 1.3, where the 3 repeats forever. So coming here, we said it's about 1.35, so that's pretty close. Now, for the purposes of graphing, we need the y values, so you would just plug in and get that. So we know 3, 0 already. The other one, this would be 4/3, 125 over 27. So even without calculus, we were able to get pretty close. And at this point, all we have left to do is just to sketch our graph. Again, this turning point, just get it as close as you can. You have the other points there. So you would just sketch this guy like this. I have a computer drawn one. So of course that's going to be drawn perfectly. Your graph does not need to be perfect. Just get it as close as you can.